Hello everyone, I am pleased to present our paper, Training for Identity Inference for Controllability, a unified approach to turning free face personalization. In this work, we studied turning free face personalization for text-to-image diffusion models. Given one or a few reference face images, our goal is to generate new images that preserve the target identity while still following diverse text prompts. As shown in the examples, the model should not only keep the person recognizable, but also supports large changes in style, pose, skin, action, and composition. Face personalization is a particularly challenging personalization task. On the one hand, humans are highly sensitive to facial details, so identity preservation must be very accurate. Small changes in facial structure can make the generated person look like someone else. On the other hand, a useful personalization model should remain controllable. The user may want the person to appear as a knight, a cartoon character, a cyberpunk warrior, or in a completely different skin. Therefore, the key challenge is balancing two objectives: high identity fidelity and strong text controllability. Existing turning-free face personalization methods usually follow two paradigms. The first is the text embedding approach. It maps face features into the text embedding space. This approach usually preserves the original text-to-image model's controllability relatively well, but its identity preservation is often limited. The second is the adapter approach. It injects face features through additional cross-attention layers as IP adapter. This can provide stronger visual conditioning, but it may weaken the model's response to the text prompts. So these two paradigms have complementary strengths, but neither alone fully solves the identity controllability trade-off. A natural question is, can we combine both paradigms and obtain the best of both worlds? Our preliminary observation shows that the answer is not trivial. When IP adapter is paired with a ground truth identity name, identity preservation improves. This suggests that text-side identity information can complement adapter-based injection. However, when we naively combine IP adapter with learned text embeddings, the model tends to overfit to the input face image and loses text controllability. This motivates our main insight. The two branches should reinforce only identity-relevant information, while non-identity attributes should still be controlled by the original diffusion player and the text prompt. Based on this insight, we propose UniID, a unified turning-free face personalization framework. UniID has two branches. First branch is the text embedding branch. We extract face features using a pre-trained face recognition model, process them with a Q-former, and map them into the output embedding space of the text encoder. The second branch is the adapter branch. It also uses the extracted facial features, but injects them into the diffusion model through auxiliary cross-attention layers. The two branches are trained separately, and they are combined during inference with a normalized rescaling strategy. The first key design of UniID is identity-focused training. Our goal is not to let the new branches learn the whole image distribution. Instead, we want them to capture only identity-relevant facial information. To achieve this, we train each branch separately on portrait images, where the face occupies most of the image, and we use minimal prompts such as a photo of a man or a photo of a woman. This design reduces the change that the new branches memorize background, pose, skin, layout, or other non-identity attributes. In other words, during training, the new branches learn who the person is, and not where the person should appear or what the skin should look like. However, identity-focused training alone is not enough. If we directly use these identity branches during inference, they can become too strong and dominate the generation process. The result may preserve identity, but it often ignores the text prompt. Therefore, at inference time, we introduce normalized rescaling for both branches. For the adapter branch, we normalize the new cross-attention output and then rescale it according to the magnitude of the corresponding original cross-attention outputs. For the text embedding branch, we normalize the predicted NaN embeddings and match them to the typical magnitude of real NaN tokens. This allows the model to keep strong identity information while recovering the text controllability of the original diffusion model. This slide explains why normalized rescaling is necessary. As shown in the figure, the newly introduced cross-attention outputs can be much larger than the original cross-attention outputs. In some layers, the magnitude ratio can reach around 26 times. This means that the identity branch can easily overwhelm the original diffusion player. A single global scaling weight is not enough because the imbalance is not uniform across layers. Some layers are extremely large, while others are more moderate. Our layer-wise normalized rescaling handles this problem by first normalizing each new representation and then matching it to the scale of the corresponding original representation. In this way, identity information is preserved, but it no longer suppresses the text prompt. We compare UniID with 6 state-of-the-art facial personalization methods, including IP adapter Face ID, photo maker, LCM, nested attention with anyone, and POLID. The qualitative comparison shows a clear identity controllability trade-off in previous methods. Some methods follow the text prompt but fail to preserve identity. Other methods preserve identity better but struggle with complex prompts, such as large pose changes, style transfer, or full body generation. In contrast, UniID better preserves the target identity while following diverse text prompts. This is especially visible in challenging cases such as masks and stylized faces. For quantitative evaluation, we report results on the test set. We evaluate two aspects: identity preservation and text controllability. Identity preservation is measured by facial recognition similarity, while text controllability is measured by cliff similarity between the generated image and the text prompt. Compared with previous methods, UniID achieves a better balance between these two metrics, rather than improving one side at the cost of the other. We also conduct a user study with 40 participants and 720 responses. Participants are asked to choose whether result better preserve the identity while matching the prompt. The user study shows a consistent preference for UniID over all compared baselines. To conclude, we propose UniID, a unified tuning-free framework for face personalization. The core idea is to separate the rules of training and inference. During training, both branches are encouraged to focus on identity information. During inference, normalized rescaling restores controllability and allows the two branches to provide complementary identity signals. With this design, UniID achieves strong identity preservation while maintaining flexible text controllability. Thank you for watching.